We'll start at 1, so yeah, we'll have 5 minutes. It's not to say that it's all like okay, but the line. Just presenting, I guess. Here you can see.
Yeah, it's linking here.
Hello. Hello. Hello.
Hello. Can you
Hello,
hear
Derek.
me?
Yes.
Oh, hi. Good. Hi.
Hi, Derek.
Hello. Hello again.
So yeah, I guess Gile can actually wait for a couple of minutes and then we'll start my presentation.
Wow. Lovely.
Just called Ian. I'm hoping he's just logging in.
Okay.
Leave the lobby. Oops, it's great turn up.
So Gilay, I think I can actually start. If you could please add, the people who are waiting in the lobby, that would be, really helpful. Is that okay?
Gulay? I think maybe we should start.
Yeah, Gilay, I think I can start. And yeah, if you could actually add the people who are waiting in the lobby.
Show like, hey, I'm waiting on certain people to move to the next step.
Hello?
So Gilay was saying that, I can share my screen, you can hear me, so I can actually start the presentation, I guess. Is that okay with you?
Yes, Derek, Derek, can you hear me?
Can you hear me?
Yes.
Right. Just to say that Professor Ying Jiangang has been delayed, and so he just asked me to quickly do an introduction, but I hardly need to do that. We've had this plan for some time, and we're very much looking forward to this particular lecture. Arcadis have a lot of experience in this area, and they are contributing to our third edition of the book on intelligent buildings, incidentally. So over to you, Georgios.
Yeah, thanks, Derek. Hi, everyone. My name is Georgios. I'm a senior building system integration consultant at Arcadis. And today I will be talking about ontologies, which is a topic that I have been working for quite some time, and how this can be actually applied in buildings, intelligent buildings. Okay, so in general, I have a vision, a career vision, if you want, which is to contribute towards one step closer to harmonization and democratization of one classification systems which are related to BIM and ontologies, which are related to intelligent buildings or semantic models or digital twin graphs. There have been a couple of names for that, of built assets, so in the built environment, in a pragmatic and cyber secure way. So I'm approaching ontologies from a practitioner's point of view, while considering the concepts coming from academia. Okay, so today, the scope of this presentation is to inform and raise awareness about ontologies based on my experience and based on what I have seen so far, and hopefully this will trigger you to use some of these concepts in your own work. So in terms of the agenda, I will talk about the drivers and use cases, the data and semantic gap in buildings, which is part of the building performance gap, some concepts about ontologies, things about interoperability, the value of ontologies, and also some lessons learned throughout the process and recommendations. So regarding the drivers, climate change, sustainability, and ESG strategies are things that more and more companies, countries are being pledged and are committed to. Having said that, a lot of them are also trying to approach the building performance concept holistically, either at their building or portfolio of buildings. So with that in mind, and the emergence of data and information that we have from IoT sensors and the emergence of machine learning and AI, we try to leverage the data that we have from the built environment so that we try to provide a holistically better environment, a better environment in terms of energy, in terms of carbon, but at the same time without compromising in the indoor air quality and comfort, okay, or productivity. So
I think, yes, here, that's okay.
With that in mind, we should actually start by the use cases, okay? And the use cases that we have is essentially stakeholders who want their buildings to be smart or net zero or sustainable. They want to control their buildings or portfolio of buildings and know where is what. Or they want a digital twin, a digital replication of the building to operate and maintain efficiently and try to diagnose issues in order to save in terms of cost, carbon, and at the same time increase productivity. But the reality is a bit different because essentially what people have in practice is unstructured electronic documents.
What are you actually
here and
trying
there.
to, is there a problem with the permit or is it you're waiting
Poor
for
data
approval?
quality and no logs. So these are what the reality is in buildings. So we have a lot of times the stakeholders been in a situation where they don't know how to deal, how to cope up with this problem. So the problem of data and information management and how we will handle all of these documents arise. Okay. So let's go now and talk about this data and semantic gap, information gap in buildings that I talked about. So the first challenge is the data and information stage gap. So it is well known that across a project life cycle, because of different stakeholders being involved, because of the fact that the project is a long process, what we have is a performance gap. And that is because we have different stakeholders dealing with the different stages. People are used to different approaches. And that leads to discrepancies between what it was expected as designed, as built, and as commissioned. Okay, subject of which is essentially the data and information gap. So what we see across the project lifecycle is data and information loss. And this is because a lot of times data is not considered in practice as an asset. Is not considered as a resource that should be managed and curated properly. And that leads to an increase in what we call a total cost of ownership of data and information. So essentially what is happening is the client is paying over and over again for the recreation of the same data, for the same information, okay? And also for the levelized cost of entity, okay? So that is happening because across the years, the same data and information is being recreated, okay? So there are some questions that arise across this challenge, which is how do we ensure continuity for the information model of the building or buildings? And on top of that, how we develop, scale, validate, and standardize all of this process. So these are questions that essentially the client, in one way or another, has to face in order to have controllability of their building or portfolio of buildings. Okay. The second challenge is related to poor descriptive information. And here we will see with an example the value of semantics. Okay. So let's say that we want to analyze this thing ZN3 WWFL4 equals 25. Okay. So a lot of questions can come. One obvious one is, what does the number represent in terms of units? Is it degrees Celsius, Fahrenheit, kilowatt, kilopascal? Then, so we need to know the units. Let's say that it's degrees Celsius. Now, okay, is 25 degrees Celsius okay? We don't know, because we don't know essentially what this essentially represents. Okay, what is it? Is it a zone temperature? Is it a return air temperature? Is it a chill water temperature sensor? Sensor is something that measures the temperature. Okay, let's say that it's a zone. Okay, now there are other things that can be related to the zone temperature, like what is the schedule for the space? Okay, let's say that the schedule is from 7:30 to 6:30. Okay, what air handling unit is it served by? Let's say air handling unit 1. So you can see essentially, as we are starting asking these questions, we are starting unfolding something which is essentially the semantic model of this particular system, but also the building as we're developing this semantic model more and more. Okay, so the question that we have is, how can I convey these answers in a standard way that other software can interpret? How we can actually make this information accessible? Because at the moment, in a lot of situations, it is challenging to really leverage all of this data and information in the building. Okay. So what we have essentially with the poor descriptive information and semantics is the fact that we are data rich. We have information overload from buildings, but we are information poor. We cannot process all of this data easily. Okay. So most data produced by device and equipment have poor descriptive information to define what the data means, what's the meaning behind of this data. There is no standardized approach. There are a number of approaches which I will present in the next slides, but there is not a standardized approach for that. Some that we need to bear in mind is that names and abbreviations, which are used a lot in the BMS industry, only can't do the job. You cannot see the complete picture from just the name and abbreviation. As you saw before, here, just by the name ZN3WWFL4, we cannot really know what that entity represents if we don't have more information, additional information about that. Okay. And as you can imagine in practice, in order to develop this model, there is a labor-intensive process to add this semantic definition before the analysis starts and the value creation starts. Okay. On the right-hand side, I have essentially two heuristic situations from where someone can really see the value of this process. Okay, so we have essentially Metcalfe's law, which shows the value based on the number of devices that you have. Okay, and the other one is the value from essentially the data. Okay, and as you can see here, this is the division of the number of devices squared by the mouse clicks to deploy, essentially the manual work that is required, okay, in order to manage to create this semantic model, this data model, this metadata schema, okay, in a satisfied level. So the more manual work, the less the value it is, okay. So in order to actually deal with that, we see that we have all of these different data silos across, the buildings across the industry, which is essentially, as we said, a time-consuming work. And usually the approach that it is being followed is a top-down approach from the system integrator or consultant in order to go through that process. Okay. But what we need to do in order to minimize this data and information gap, okay, is to start following a bottom-up approach, okay, so that we have tags, we have information, we have data about that data, okay, on the device level, but also when we are going through the different RIBA stages, the design stages along the way, okay? So the earlier we adopt this idea and we consider the data and information gap that exists in buildings, the less costly it will be for the client and the less work it will need to be in order actually to achieve his goals, their goals, whether that is for ESG, sustainability, or intelligent buildings. Okay. So we need to build a semantic model, okay, which is essentially all of these terms, rules, categories that allow you to define the semantics, okay, and define the relationships between different entities. As you can see here in an example, we have the different entities that have a relationship to each other. For example, on the right-hand side, you can see the point ID has, the airtemp has a time series ID, point ID. The airtemp is tag of. So we have these relationships, as you can see, okay? So this ensures that we have a model ready for analysis, for optimization. So this model, which is the ontology, semantic model, the metadata schema, is what essentially bridges the gap between the physical layer that we have and the digital layer. Okay, so we need this data model, this information between the entities and relationships at different levels. Okay, from location, system, equipment, point to a satisfied level. Okay, so that we start meeting our needs, meeting our use cases. Okay, having this metadata schema, this semantic model, will allow us to go to the management layer when we can actually store our data using different APIs, starting doing queries, starting saying how many different unique systems Can you hear me? Because I was muted. Yeah. Awesome. Yeah.
No, it's fine.
So we can essentially control what we can measure. So if we have this semantic model of the different concepts that we call them in between systems, equipment, points, then zones, we can actually start querying and deriving into insights and information for our building. Okay. So now let's move on to ontology. This is a big topic, and I will actually talk about the definition at this point and some of the components that I believe we need to bear in mind when we are dealing with ontologies. Okay. So ontology is essentially the rules and standardized terms, categories, definitions, and other descriptors that semantically describe an information system. This is according to a definition that based on Google Digital Building Ontology. Okay, so this definition here can be a bit confusing. So let's try to start decomposing and see some of the main components, in my point of view, that someone needs to bear in mind when he's dealing with ontologies. Okay. So the first component, which is also a problem in the industry, is definitions. Okay. We need to give our tag names, our terms names, so and have formal definitions as terms. Okay. That ensures that everyone is on the same page through a controlled vocabulary. Okay. We have definitions in place. That means that an air handling unit is the same thing for the contractor, the same thing for a designer. Okay. So this is one of the first things that needs to be considered, the definitions, how we define the different entities that we try to define for our building, for our instance model. Okay. This is okay with the definitions, but are definitions enough? The question that we have then is, let's say that we have equipment. How are these different terms organized? Because we have the definitions, but we need to give some structure, okay, in order to see how these terms are organized. Okay. And this is where essentially taxonomy comes into play. Taxonomy is nothing more than a tree that organizes these terms that we defined, okay, from general concepts, okay, to more specific. So on the right-hand side, you can see an example where of a taxonomy. So we have essentially the general concept of an air handling equip. This is based on Project Haystack. And then you can see the different subtypes of this air handling equip based on Project Haystack. Okay, so you can see that these is actually split by air handling unit and fan coil unit. The air handling unit has different subtypes, and all of these different entities as well have definitions associated with them. Okay, so we said one, definition, define our terms. Two, create relationships between the different terms that we actually defined. Okay, here I'm showing essentially graph from Google Digital Building Ontology describing the general concept and the specific concept. So we're going from the general concept where on the right-hand side, you can see the concept of equipment, okay, to a more specific one, which is the concept of VAV, the one on the middle, okay. And then on the left-hand side, you can see essentially the concept of VAV1, which is an instance of VAV type, okay. So taxonomy allows us essentially to do that, to define these sort of relationships. And that's okay, but then how are other concepts related? So how about concepts beyond taxonomy? In our buildings, we have different entities, different concepts. We have the concept of zone, with location. We have a concept of equipment. We have the concept of points, sensors. So how are these concepts related to each other? Okay, we have the concept of substances, okay, and units. So because of this heterogeneity that we have, okay, we need to actually go beyond taxonomy, okay. So an example which can be taken as a use case, I want to define the relationships between equipment concepts and points, okay. So essentially ontology is concepts beyond taxonomies, okay. So here, essentially, I'm showing the ontology, okay, as a form of a boiler template of the elec meter, the concept of electricity meter. Okay, so these are essentially the potential points an electrical meter can have. Okay, and this in practice can be used based on different specs, verticals. So there is a specification for electricity meters in Project Haystack. Okay, or templates, custom templates from the different people that are using this. So they can take essentially the Project Haystack and use it the way they want. Okay, add some points and so on and so forth. Okay, which can be from Excel spreadsheets to more sophisticated and advanced data formats. Okay, YAML file, JSON, and so on and so forth. So now to actually go to some examples. So the first one is about Project Haystack. On the left-hand side, you can see the different concepts and how these are related to each other. This has the ending ref on the end in order to show the relationship between point and equipment, equipment site weather. There are more concepts. These are just for illustration purposes to understand how that works. There is system, there is zone, there's also other concepts in Project Haystack. And on the right-hand side, you can see how these are related to each other. Okay, you can see examples where we have the instance model for device and a chiller. Okay, and you have essentially an ID for each entity, a human readable display name, and some metadata and the relationships about that. Okay. Another ontology is Brick, which is what they call ontology-based metadata schema. And here we can see that the relationships are more sophisticated, as opposed to Haystack, where we had essentially the concept of containment using the ref, ending ref for the relationship. Here we have more specification around the relationship between the different entities. Okay, so as you can see, for example, we have the instance air handling unit AHU1A, which is essentially type air handling unit. This air handling unit 1A feeds VAV23, which is of type variable air volume box. This feeds a VAV23 zone. Okay, and this starts again, being unfolding more and more and more. Okay, now how this can be used? This can be used in different ways. Okay, from starting querying, okay, and saying how many different VAVs I have, how many different zones. So starting doing some descriptive statistics around that to doing more advanced stuff. Okay, doing fault detection and diagnostics, tying essentially time series data from the sensors, actuator, all of these different points, and starting seeing the profiles and try to identify, diagnose issues for this, for the building that you have. Okay, I will talk about some case studies later on, but I just wanted to actually give you some examples as well here on how this can be used. Okay, real estate core is another ontology which is used a lot in real estate. There's a harmonization between real estate core and brick. So here, apart from essentially the equipment, you can actually see the equipment, the zones. You can actually see information about the tenant, about the building. But essentially, it has the same kind of principle. Okay, so we have definitions, taxonomy, and ontology associated with that. Okay, now another example is the ontology alignment project, which is essentially a project-driven initiative that aims to extend the methods and tags already defined in Project Haystack and Brick Schema. Okay, there are entities that have not been defined from Project Haystack as it is an open initiative. And for that reason, a lot of different actors in the market have decided to try and support, join the cause and support by try to define the other entities that are not defined, and also try to harmonize and show the equivalent entities or concepts in other ontologies. Okay. Another example of ontology is quantum, whose goal is to have a holistic autonomous controls and system engineering based ontology. So this is a more advanced ontology, I would say, that takes into consideration as well the purpose and the controls and system engineering approaches from the buildings as well. So it also considers the physics associated with that. Okay. So a lot of ontologies, a lot of them have advantages and disadvantages, for which I will talk later on. But a very nice comparison that was actually done earlier this year, that was published by the Annex 81 Data-Driven Smart Buildings, which I recommend you to have a read if you're interested. So they actually compare the most common metadata schemas based on 4 elements. Okay, tagging, metadata, linking data, and semantics. Okay, so in other words, adding tags and some information, trying to add additional information and use some of the ontologies, linking the different data and going through a more sophisticated semantics approach. Okay, so as you can see, most smart buildings are closer to the tagging element. And the reason being is because most stakeholders in practice trying to apply some of these concepts, okay, but at the same time there is a lot of custom approaches along the way. Okay, so that's why you see essentially that most smart buildings, based on my experience, are closer to the tagging method, they are not close to applying the different ontologies like rec, real estate core, brick. You know, I'm not saying that these are not being applied. There are vendors that are applying real estate core, brick, and other ontologies, but it is challenging for the industry to really apply, scale, and standardize this process, let alone democratize. Okay, which means, if you think about it, that essentially one, data is not considered as an asset as it should, and two, there is not clear ownership of the data that of our buildings. For me, ownership means I'm controlling the data and the information that I have in my buildings. Okay. Now, a very nice comparison between the different metadata schemas from the systems that they actually they have defined, which can be found in Brick Schema's website. You see essentially the different systems. This is not metadata schema. Apologies for that. It's essentially the different systems and relationships. And if the different ontologies have considered these systems in their approach. Okay, as you can see, Brick and Google Digital Buildings are the ones that have considered most of them, but also the others are have considered in their own way. Okay. Another comparison is compared to based on the naming, tagging, and the different graphs. Okay, so essentially, does the ontology consider defining names for the different entities? Does it consider tags, key value pairs, or just a word to define the tag, a fact, and additional information about the entity? Is the format that is considered tabular, a table? And we have also graph and RDF ontology, which RDF ontology is the one that is agreed from the industry to be the get-go for most ontologies. Okay. Going back to the project lifecycle, there is essentially a paradox here where you have on the one side the digital twin vendors and O&M domain where they consider APIs, they consider RDF format, they consider all of these formats that can really work in software architecture and solution architectures. However, because the project life cycle of a building is long, and essentially a lot of the stakeholders are engineers, are people, consultants are people who are used to working with tables, with tabular data. Okay, so there is this, I guess, challenge of trying in practice to agree on a format that people can work on in order to have, as I said in the beginning, the semantic model, a complete picture of how the entities and relationship, or a just enough picture of how the entities and relationships are in the building or portfolio buildings. Okay. Now, a comparison in terms of harmonization, as I said before, Brick was harmonized with real estate core, but essentially a lot of ontologies like Brick, Google, digital building ontology considered K-Stack and other ontologies in order to actually define their own one. Okay, so in some cases we have alignments, in some others there's not something that it actually took place. But what it needs to happen essentially at some point is to, and it has already started from people in the US, is to try and harmonize all of these different ontologies so that people have the option to easily create this semantic model and make their lives easier. Okay. Now going to interoperability and essentially the software architecture, what it is, I would say, seems to be a general pattern. Okay, for the essentially the data pipeline is to have the data that you receive in 3 different layers. One is around semantics, giving meaning, the ontologies that I actually talked about, site, equipment, point, zones, so on and so forth. So this is essentially the model, the skeleton, the digital twin graph of the building or portfolio of buildings, if you want to scale. Okay, and these are stored in essentially triple stores, which is essentially the concept of having a subject, predicate, object approach sentence, like the ones that we saw in here. Okay, Erhan unit 1A feeds VAV 2, 3. Okay, this kind of approach. Then once we actually go into the operation stage, we start having time series data, temperature, humidity, data from meters. So we need essentially to find a way to bring all of this data in one place, okay, and align them based on the scope and the need that we have, okay. And the third element, which is important, is essentially the control system, including the control logic of the building. And this refers to all of the different algorithms, okay, that essentially orchestrate how this data, how the building operates, essentially. Okay, so these are the 3 elements. Of course, there are more things here. Okay, there is essentially the process of transforming the data. Okay, there are different ways to do that, of course. Okay, but these are essentially the 3 main things that will allow, once you actually integrate them into the data layer that I talked about previously, you will be in a position to start meeting your needs, whether it is on building diagnostics, energy intelligence, demand side response, or net zero. Okay, and this is based on this was under also Annex 81, data-driven smart buildings have actually concluded based on their research. Okay, now the value of ontologies, essentially what we have as a value is time efficiency and standardization. Okay, it is a time-consuming process, but essentially once you have that, you can save time and effort because you established the naming conventions and or the taxonomies that we talked about, these 3, okay, that will allow you not to start from scratch. Okay, and standardization is important. And on the right-hand side, I have a very nice example from Google Digital Building Ontology. Okay, let's say that we have essentially a cloud application, okay, where this manages a lot of buildings, okay. And this essentially sees 3 different names, zone underscore temp, SNT, zone underscore TF, okay. And these, because of the names that you have, the inconsistency in the names, it's very difficult to actually answer the question, what's the current zone temperature for all devices with that sensor? Okay, so it will be difficult to answer that if you have this inconsistency in your naming convention, okay, in your approach, essentially, okay. Just an example to demonstrate the value of ontologies if that takes place, okay. It's not an easy process, but once it's done, because it will be done once, and then there will be essentially a process of curation and addition and all of that, you will really start getting the value from your building. Okay, and this starts essentially, once you have that, you can actually start applying engineering expertise. You can start applying domain expertise, okay, in order to validate observations and really control your building, okay? It's not just about assessments, okay? We need deep design rigor, okay? So once we have this data model, if we have this essential infrastructure, then we can actually start combining that with engineering expertise and advisory in order to pragmatically add value and have impact and help our clients, the things in buildings. Okay. So, some of the examples where essentially ontologies can help. If you have essentially the data model, you can spot on problems easily. Okay, problems like, for example, negative CO2 sensors, dampers that are working, for example, 24/7 and 100%, which are things that maybe some of you might think these things should have been actually identified earlier. Yes, they should, but if you don't have this model, this semantic model, it is really challenging to validate, to see this problem in practice. Okay. Another example from a university campus in the UK, where essentially, because we have this semantic model, here you can see different entities, right? You can see buffer vessel, high level temp. You can see, for example, cooling demand, stage 1, stage 2. We can profile, okay, a lot of different equipment sensors, and as a result of that, equipment systems together. Okay, and that allows us to correlate the different entities in our building and really starting diagnose problems for our building. Okay, and that's why I'm writing here, you can't diagnose and improve what you can't map. Okay, ontologies, control, analyze, building analytics and control logic, and measure and monitor, where you actually add more the engineering expertise along the way. Okay. And this is essentially the general pattern, which was actually was found based on observations on site, but also the data that we received from the BMS system. Okay. This is another example where we actually added the carbon intensity from the national grid. We integrated the API and we find essentially avoidable carbon. Again, these things calculated entities, essentially virtual entities, can be added as well in the data model. Okay, and now we'll go to show you an example to show you how essentially a company thought of approaching leveraging the semantic model, okay, in order to control their building. Okay, there's the case study of Saffron AI, which is an AI platform for commercial buildings developed by 75 Fahrenheit. Okay, and these guys essentially what they have is a chatbot, which on the back end has more or less the software architecture that I presented previously. Okay, and using some more advanced approaches as well. Okay, they start asking essentially this chatbot, and also they can give back to that, commands to the building. Okay, for example, here there's a question that you can see which zone has the worst indoor air quality, IAQ. And you can see because we have essentially the infrastructure with the semantic model in place, it can give us an answer. Okay, then you can actually, do more things as well. I mean, this was just, an example where they said answer like a scary pirate. Okay. On the right-hand side, you can see, for example, they ask change the desired temp, okay, to 72, and then you see essentially the chatbot asks, should I proceed with the change? And then essentially the person said yes. and it actually makes the change back to the building. So this is a nice concept where we can see how essentially machine learning approaches can be used, okay, in commercial buildings in that case, in order to start controlling the building. And in practice, this can be potentially a valuable tool for facility managers, because the facility managers in that way can control and manage all of these plethora of equipment systems and sensors and systems in the building easier. Okay. So, conscious of time, lessons learned. Data is an asset, so we should treat it like one. Ontology is essential for holistic building performance. We need to embrace the difference of ontologies and combine them accordingly. And we really need people who combine engineering, data science, advisory, management, consulting, and technologies. Okay, we need people who actually understand the different domains and can talk, these sort of languages as well. Okay, in order to leverage all of these concepts to the level that they can. Okay, so here I emphasize that is an asset, so we should actually treat it like one. And here's an analogy where I compare essentially the asset of data to the asset of real estate. Okay, so while the initial asset holds inherent value, it requires additional effort and upgrades to increase the value and create value out of it. Okay, so you can say here, for example, the comparison, I think is self-explanatory here. Okay, and here is essentially the thing that I said about the amalgam of domains. So we need essentially engineering expertise on the top, advisory on on the bottom, engineering layer on the bottom, advisory management consulting on the top. Then we have essentially the BMS and controls layer, the data layer, which is classified into textual data and time series data, where textual data is ontology, define the semantic model of the building, and building analytics, analyze meters, sensor, and/or IoT data, which can then have digital twins, analytics in terms of IoT and meters, which is the digital twin intelligent layer. Okay, and all of that cannot work if you don't consider technology, processes, finances, as well as people. We need to be people-centric when we actually try to adopt this concept of ontologies and anything associated with intelligent buildings. So why ontologies in buildings? You can control what you can map, ontology. You can control and analyze what you can measure and monitor, building analytics. And you can diagnose and improve what you can map, control, analyze, measure, and monitor, building diagnostics and FTD and other applications. Just for in the end, I just want to say that I'm leading a working group in Project Haystack, where we're trying to align Haystack with IFC and BIM. So please join the cause if you are interested. Everyone is more than welcome to contribute in this initiative. Thank you very much. Sorry for taking so much time. I hope that was helpful and you actually took something from all of that.
Thank you. Excellent presentation. Probably most of our audience haven't had any question yet, but if you have any question, please just type in the chat area, or you can unmute yourself and just introduce yourself and ask a question. Later on, we'll try to share the recording on CPC website and also the PowerPoint presentation. We will have another bi-monthly webinar, and then we might have a more informative kind of discussion with Grigoriou. Okay, so the floor is yours. If you have any questions, just please unmute yourself. Thank you. Or probably in the chat area, there are a couple questions. Grigoriou, do you mind to
Yes.
look at the chat there? Thank you. Cheers.
Yes. So there is one. I see. I don't have the real explanation. Yeah, I mean, there's a very good observation from Andrew. So essentially, yeah, a lot of times, unfortunately, we don't have this feedback loop from operation to, design. Okay, there are lessons learned, okay, but a lot of times in practice, these are not considered, I would say. Okay, so the straight line was, I would say, more for explanatory purposes. Okay, essentially the main point from that slide was that you have this performance gap as a result of, and there is contribution of essentially the data and information stage gap throughout that process. Okay. I don't know if I actually answered the question, but yeah, this is what I saw in practice happening, Andrew. A couple of questions. So, do you think that the SSN and source ontologies are worth it again? I mean, I would say there is not right or wrong answer in terms of ontologies. Each one of them serves a different purpose. Okay, for example, Project Haystack is very flexible. Okay, but at the same time, because it's flexible, a lot of people are confused. They want something more robust. Okay. On the other hand, there is, Google Digital Building Ontologies, which is quite comprehensive. Identifies the fact that when you actually develop a semantic model, you need also to have a mechanism to validate the model in terms of the engineering side of things, that the things that you actually put in the model make sense, but also from an ontology. So do we really do that according to the ontology that we are saying we're using? Okay, so I think the most important thing is to define the use case, and based on the use case, okay, then you need to actually select the most appropriate ontology or combination of ontologies. Okay. Other questions? There's someone who.
There's a question from Brian. Okay.
Yes.
Brian,
Yeah.
Yes. Thank you.
Hi, Georgios. Hopefully you can hear me okay.
Yeah. Yeah.
Thank you for the insightful presentation. Really appreciate that. My question is, I'll have a quick one whereby I think a few people still seems to wonder why we still have so many ontologies, or maybe people looking at producing new ones as we go forward, rather than maybe collaborating all of us together as maybe a team to now put everything that's available to maybe interconnect or be able to support all the systems that are available in building. Is this something that you see is going to be happening at any point soon?
Yeah, I mean, essentially, you have all of these different ontologies serving the different purposes, and you ended up having, as you correctly said, a number of them. And even, there are classification systems that I didn't talk in this presentation. And now, what people are doing, and there's a very big attempt, especially from the Department of Energy in the US, to essentially harmonize all of these ontologies. Okay, there is the concept of building motif, which is essentially this idea of harmonizing and providing semantic interoperability across the different ontologies. Okay, now this is essentially a question that I feel more and more that is a matter of habit, because essentially when you say that you will align with an ontology, you need to align with the three main components and other things, but essentially the definition, the taxonomy, and all of that. And it's very difficult for people to align sometimes when they are used to other approaches. Okay, especially when people are super busy with a lot of projects. So I feel that we are now going through a way where we're trying to harmonize all of these approaches, and this will give essentially the opportunity and the tools, okay, to help companies, clients, people to leverage the power of ontologies. This is what I have seen from my view, from my experience. I know we're out of time. Yulei and Jan, if you could actually send me, the questions, I'm happy to answer to all of them when I will be available.
Yeah, that's great. Thank you. That's
Yeah.
wonderful presentation.
Thank you.
Get in touch. Many thank you.
Thank you very much.
Thank you.
Thank you.
Bye
Bye bye. Bye.
Bye. Bye.
Bye.